Hello everyone, and today we are going to go through FRQ 3 of the momentum FRQs. And our FRQ is block A of mass 4 kg is on a horizontal, frictionless tabletop and is placed against a spring of negligible mass and spring constant 650 Newton meters. The other end of the spring is attached to a wall. The block is pushed toward the wall until the spring has been compressed a distance x as shown above. The block is released and follows the trajectory shown, falling 1.8 meters vertically and striking a target on the floor that is a horizontal distance 1.2 meters from the edge of the table. Okay, so let's start with part A. Calculate the time elapsed from the instant block A leaves the table to the instant it strikes the floor. So first we are trying to find from where the block is right here to right here. And let's just list everything that we know. We know that the table is 0.8 meters. We know that velocity initial would be 0 since it starts from here. And we know that since the block is falling, that it has an acceleration of 9.8 because that is what gravity is. And let's just list that all right here, which I have already actually. And then final thing to list is t, which we don't know, so we are going to put a question mark on that, and that is actually what we're trying to find. So let's take back to our information from kinematics and use kinematic equations to solve this problem. And the equation we are going to use is So we are actually going to be using the kinematic equation y equals y naught plus v naught t plus 1/2 a t squared. And then from here we could just plug in the values that we already listed above, which is 0 equals 0.8 plus 0 times t plus 1/2 of 9.8 t squared. And so we could just simplify that and compress the equation. Since we know that 0 times anything is 0, we could just cross that one out, which cancels out our first t variable. And so that would be 0 equals 0.8 plus 1/2 of negative 9.8 would be negative 4.9 t squared. And since we're trying to isolate t, because that is what we're finding in this equation, we could just minus 0.8 on both sides, subtract on both sides, and then negative 0.8 equals negative 4.9 t squared. And again, we can isolate that t even further, so we're going to divide by 4.9 squared t squared. Oh, not t squared. Erase that. We're actually just dividing by negative 4.9, negative 4.9. And since these values are both negative, it cancels out the negatives, and the result, the answer turns into a positive. So then we get t squared equals 0.8 divided by 4.9. And then to get rid of the square, we just have to square root on both sides. And then we get the square root of 0.8 over 4.9 equals t. And so then the answer is 0.4 0.404 seconds is equal to the time. And so in conclusion, the time it takes for the block to fall from the table is 0.404 seconds. Booyah! I also wanted to point out that there is actually a much easier way to calculate time for part A, because there is a quote-unquote shortcut for this problem, and it is t equals the square root of the height over 4.9. And as you can see from the last part, this is literally the equation that we got from deriving the equation to isolate t. And so you could just plug in the height of the table, or like at whatever height an object is falling, over 4.9, and you would get your answer. Okay, now moving on to part B. Calculate the speed of the block as it leaves the table. This part is actually quite easy. All we need to do is just calculate v equals distance over time. And this is easy because we already have the answers to both d and t, since we got t in part A, which was 0.404, and distance is actually a given because it says it here, 0.2 meters. Since that is the distance it falls, we could just plug that in to the equation. So v would equal 1.2 over 0.404, and that would actually equal to 2.97 meters per second. And so the speed of the block as it leaves the table is 2.97 meters per second. Okay, now on to part C. Calculate the distance x the spring was compressed. So now we are trying to find this distance x the spring was compressed, and we will now be using the given 650, the spring constant, in our equation. So with this, we are going to be using conservation of energy, and we will be using US equals K. And U spring is 1/2 kx squared equals 1/2 mv squared. And since we're trying to get the distance x the spring was compressed, we just need to isolate x and derive the equation so we could get x by itself. So in order to do that, we will have to 1/2 k divide 1/2 k on both sides, and so 1/2 k will cancel out, and this will cancel out that 1/2 on this side, and that would leave us 2 squared equals mv squared over k. And since again we are trying to get x by itself, we would just have to square root on both sides, and then you would get the final equation, which is mv squared over k. And since we already know all of these values, m is a given, which is 4 kg, so it would be 4. And then since we already found the velocity from the last part in part B, we just plug that right in. Oopsie, I wrote a 9. We just plug that right in, 2.97 over the spring constant, which is also given, which is 650, and then you could do x. And that calculates to 0.233 meters. So in conclusion, the distance x the spring is compressed, this number, is 0.233 meters. And that concludes the first part of FRQ number 3.
This is the explanation of part D of FRQ 3. Now, before we can jump right into the problem, we have to look at a new scenario provided to us. Luckily, it is just an adaptation of the previous scenario. It is as follows. Block B, also of mass 4 kilograms, is now placed at the edge of the table. The spring is again compressed to distance x, and block A is released. As it nears the end of the table, it instantaneously collides with and sticks to block B. The blocks follow the trajectory shown in the figure below and strike the floor at a horizontal distance of d from the edge of the table. Now, there's a lot of important information packed into here that we should take note of. Firstly, it being that this spring is still compressed to the same amount as previously. So that means this block A will have the same velocity that we calculated for part C. In addition, this is still the same table, so it's still the same height, and that means that we'll still have the same time that we calculated in part A. Furthermore, still the same, since it's still the same situation, the situation with frictional forces is also the same. That means that there's not going to be friction in the air or friction on the table, so it's going to be still a closed system. And now question D itself is calculate D if x is equal to the value determined in part C. And so, well, one might think that's just quick kinematics. I mean, well, the kinematics itself is quick and easy. We can't just start plugging in right now. Because, well, yes, we already did calculate an initial velocity. That initial velocity, we can't use it for this problem. That's because of one key fact mentioned in the description, is that the blocks stick together. And so, what does that mean? So this kind of collision is called an inelastic collision, and in this case, it's perfectly inelastic. And so, inelastic collisions do not conserve kinetic energy, which is velocity. And so that means the blocks, once they've stuck together and collided, are going to leave the table with a different velocity than before. So how do we calculate that velocity, one might ask? Well, luckily for us, the conservation of momentum allows us to do that. Well, inelastic collisions don't conserve kinetic energy. Luckily for us, all kinds of collisions do conserve momentum. And there are equations with which we can solve for momentum. And so the conservation of momentum states that the initial momentum will be equal to the final momentum, and the initial momentum is composed of is from adding up all the momentums of each block, and the final will be the adding up all the momentums of the blocks in the ends after the collision. So we can say that m1 mass 1 times velocity 1 plus m2 times v2 equals m3 times v3. Sorry, m1 times v3 and m2 times v4. However, also, since the blocks stick together, we also have to remember this, that now that they're stuck together, they're going to be traveling together. And since they're traveling together, each block will have the same speed. And so that means that v3 and v4 are equal to the same thing. So we can write them as just v3. So we can say, make that side of the equation just m1 v3 plus m2 v3. And factoring out the v3, we can get m1 v1 plus m2 v2 equals m1 plus m2 times v3. And that is now an equation that we can easily and quickly solve because we also have the values, many of these variables. The problem stated that blocks 1 and 2 have the same mass, that being 4 kilograms, so m1 and m2 will both equal 4. In addition, because the first block is still released from the same spring with the same compression and the same spring constant, it will still have the same initial velocity. That being, as we calculated, 2.97 meters per second. So that will be v1. And v2 is the velocity of the second block. And this second block is just placed at rest at the edge of the table, meaning that it will have an initial velocity of 0 meters per second. And v3 is unknown. It is a variable we're going to be solving for. So if we plug all of this in, it's a pretty simple equation to solve. We move everything to one side, and in the end, the result is that we can know that the v3, the final velocity of both blocks, is going to equal 1.458 meters per second. And now finally, after all that work, we can move on to the next step in our calculations, the kinematics part. And so since this block, these two blocks, they have a different initial velocity, but this is still the same table, still the same scenario, so they're still launched at the the horizontal, meaning that the only component of their velocity, initial velocity, will be in the x direction. And so we already calculated that with our momentum scales. So we know that the initial velocity, v naught, is going to equal 1.485 meters per second. In addition, as already stated in previous parts, because this is moving in the horizontal direction, it's not going to feel the acceleration due to gravity. That's only the y. In addition, the frictional forces are still non-existent, so those aren't going to change its velocity. So the acceleration is going to equal 0. So a is equal to 0, and the initial, since nothing's going to change this velocity, the initial velocity will equal the final velocity. However, well, it is good to know we don't need to use it again because of the flexibility of our kinematics equations. Um, Furthermore, as calculated in part A, the time is still the same height, still will fall for the same amount of time, will be 0.404 seconds. And now, in terms of the two last variables, x naught and x. If we think about it, we can think about the edge of the table as being the initial position, the 0. So we could say that x naught is equal to 0 meters. And we know that the blocks will travel a distance, denoted as d, before they hit the ground and stop moving. So we can say that the final distance, x, is going to be d and is our unknown. So that is what we're going to solve for. And so using these variables, we can easily use the equation, which turns out to be the same equation we used multiple times previously. And that is x equals x naught plus v naught t plus 1/2 at squared. And so we plug in, luckily for us, x is already on one side of the equation. And in addition, two of these terms will, because of multiplication or just their value, will become 0. So we just have one simple multiplication to solve for before we can know x. And so plug that into your calculator and you will find that x, or which I denoted as x here, which the problem asked for d. So the distance that the two blocks will travel before hitting the ground is equal to 0.6 meters. That is the end of part D of FRQ 3. This is the explanation of the final and fifth part of FRQ 3, that being E. The question is the following. Consider the system consisting of the spring, the blocks, and the table. How does the total mechanical energy in E2 of the system just before the blocks leave the table compare to the total mechanical energy E1 of the system just before the block A is released? And so in this more open response question, we can use math, we can use logic to answer it. And well, I'm going to use both to explain it. I think that we can best understand it initially by using the conservation of energy, or seeing if the conservation of energy applies, so we can understand the mathematical basis before we get into the nitty-gritty details. And so for the conservation of energy, this presents two scenarios. The initial scenario just before block A is released by the spring, and the final scenario just before the blocks just before they leave the table already having collided. And so while it asks for the mechanical energy of the block just before it's released by the spring, meaning the potential spring energy, we can also think of it as it would also translate to kinetic energy. So we did, which we did use in a previous problem. We did demonstrate it at least. And so if we say that the initial kinetic energy which will be E1 is equal to the final kinetic energy. We can set them equal to each other, and we can see if they do indeed equal each other and if energy is indeed really conserved. And so what we'll have is the two equations, which is 1/2 m1 v1 squared equals 1/2 m2 v2 squared. And so before we solve, we have to establish what these different variables are. So M1 is will be block A, just block A, which is established to weigh 4 kilograms. In addition, M2 is after the blocks have collided. They've collided and become one unit, one block, and those two each block weighs 4 kilograms. So in total, they'll weigh 8 kilograms. For the V1, the first velocity, just immediately after block A has been pushed and released by the spring, it will have all of its spring energy converted to kinetic energy and thus velocity. And we did calculate that in an earlier problem, part B, and we determined that um, that velocity is equal to 2.97 meters per second. And then for V2, that is the velocity of the blocks right after they collided and become one. And from a previous part, it was calculated, part D has calculated that this velocity is 1.485 meters per second. And so if we, so with all of these known, we can plug it in and solve. And in the end, we'll get around 17.6 on one side equals 8.8 on the other side. But that is not true. 17.6 does not equal 8.8. So that proves to us that energy is not conserved in this. And that, in fact, the initial energy E1 is greater than the final energy E2. And so now that we know that, we can think about it and talk about it in its more conceptual form. So why is this? Well, friction, we established that friction is not a problem, and it's not because it doesn't exist. It's not going to decelerate or slow anything down or take any energy out of the system. The difference between the just one block and the two blocks is that just one block is always moving. It doesn't collide with any other block. However, the two blocks together, as seen in part D, they collide inelastically and stick together. This perfect inelastic collision, as previously discussed, does not conserve kinetic energy and it does not conserve velocity. While the momentum is conserved, the blocks will slow down due to a variety of reasons. The energy just doesn't disappear because you can't create or destroy energy. The energy is just turned into different forms. When the blocks collide, they might transfer kinetic energy to their molecules. This kinetic energy of molecules is what we call heat. So the blocks will heat up. They'll transfer kinetic energy to the molecules in the air. That is just sound. It will create sound waves, which will hear the collision. And also, when the blocks hit each other, they might cause a little bit of damage. It does take energy to break bonds and damage things, and so a bit of energy will be expended there. And so while it is still a closed system because of the collision, kinetic energy is not conserved, and thus the total energy differs between the initial and final moments. And we have justified how E1 is in fact greater than E2 and thus deserves this check mark. That is the end of part E of FRQ 3 and the end of the whole FRQ.